Hi again everyone, Chris Tisdell here. In this presentation I'm going to continue my series of videos that give a basic and very gentle introduction to vectors. Now in this video we're going to discover how vectors can be used to describe curves. And we're going to start with the most basic case. We're going to concentrate on a line. So how can vectors be used to represent or describe lines, and what are the associated equations? So let me share my screen with you and we'll get started. So in previous videos we've been introducing what a vector is, how to add and subtract vectors, scalar multiplication, and a few geometric understandings associated with vectors. So now we're going to progress to, I guess, another level. We're going to talk about the relationship between lines and vectors. Okay, so we can apply vectors to obtain equations for lines and also for line segments. For example, let us look at the following very important parametric vector form of a line. So suppose I've got a line L, and that L is the line L is parallel to a given vector V. So down here, the red vector would be the vector V. And suppose the line L also passes through a point A. This would be the point A in this picture, with position vector OA, or this lowercase a. Now, the claim is that the line L has the following equation. The vector x equals the vector A plus lambda times the vector V. Okay, so let me just sort of break this down into the two-dimensional setting, because people are very familiar with lines in two dimensions, y equals mx plus c that you see at school, and try to break this down a bit. So in 2D, or in the xy plane, the point A would have, say, coordinates A1, A2, where A1 and A2 are just numbers, and the vector V would just be a two-dimensional vector with components V1, say, and V2. And the equation up here would be the following. The vector x would mean the vector column vector xy, and it would be A1, A2 plus lambda V1, V2, where lambda comes for all lambda in R. Okay, so in here and here, lambda is just a real number, and it's known as a parameter, so it can vary over the whole real line. So you have scalar multiplication going on between this number and this vector. Okay, so let me develop this a little bit more as an example. Suppose I had the parametric vector form given by the following equation. Okay, so this would describe the line that passes through the point 1, 3 and is parallel to the vector 3, 3. Sorry, let me fix that up. 1, 3, and is parallel to the vector V. Okay, All right, now this definition is not limited to 2 dimensions. You can have, the x vector representing the column vector x, y, z, and then these vectors would have an extra component, a3 and v3. But it's easy to start in the 2-dimensional case because we're all familiar with y equals mx plus c. Now, why is this the form of a line? Well, what we're trying to do here, let me talk about that now, is to come up with an expression for the position vector of this point big X, or the vector O big X, if you like, in terms of things that we know. Okay, so if I move this big X point around, I can trace out the line, right? And to get to X, I can use a triangle law. If I know a point on the line, I can form the vector OA, that's just this vector here. And if I know a vector that's parallel to the line, to get to this point X, I just stretch, in this picture, I'd stretch the vector V. So it's a bit longer, and it just gets me up to that point. Okay, now just by stretching and compressing V, I can get to every point on this line. So, and then just using the triangle, this equals this plus whatever the scalar is times V. That is the equation for the line. Okay, so let me give you a little GeoGebra explanation here too. So let me just see if I can share that with you. Okay, so you can see in this picture I've got the line y equals x plus 2. That's the green line here. And x is an arbitrary point on that line. And I'm really interested in computing the vector OX. In this case, I've labeled that the vector R. Okay, so let's choose a point on that green line and form a vector to that point. Now, if I take a vector that's parallel to the green line and say it goes up to this point B, watch what happens if I want to get up to that point X, big X. I just stretch the vector AB. Okay, and to do that, I just essentially multiply that by some scalar or some number. Okay, what happens if the X was down here? Well, I'd have to take this vector and flip it, and then compress it a little bit. Okay, so that would be multiplying by a negative scalar number there. Okay. Now, one thing that puzzles a lot of people is that the parametric vector form of a line is not unique. You can have an infinite number of ways of describing or parameterizing a line. Let me give you another example. Suppose I've got a C, let's get rid of these, and let's put the point C in here. And let's draw a vector from the origin to C. Okay, and now let's put in another vector that's parallel to the green line. Okay, I think that touches, does that touch B? Yes, it does. Okay, that's not important. But here, C is a different point on the line, and the vector W is not the same as the vector V before, but I can just stretch that or compress it to get anywhere I like on that line. So if I use that setup, the parametric vector form of this line, y equals x plus 2, would be different from any other parametric form I came up with. They'd be equivalent, but they'd be different. They'd just be slightly different. Okay. All right. So let's do another a little bit of an example, and let me show you the relationship between this kind of form, at least in 2 dimensions, and the form y equals mx plus c, because it's a good question. What's the relationship between these two things? Okay. let me share my screen with you. All right. All right, so in that picture, I had y equals x plus 2. Okay, now just say I'm given that form, how can I get the parametric form? Okay, to rewrite in a parametric vector form. Now it's a parametric vector form, not the parametric vector form, because there's lots of different ways of doing this. Or you can do the following. We can let x equal this parameter lambda, and then write y in terms of lambda. Okay, now from these two equations I can form my parametric vector equations. Okay, if I take out, say, the following lambda, then I have the following vector form. Okay. Okay, so what does this say? This form says, again, that this line up here passes through the point 0, 2, which is just the y-intercept, and is parallel to the vector 1, 1. Now that's essentially that means that the line has slope 1 or gradient 1, which it does. Okay. Now, what happens if you wanted to go the other way? Okay, you start with a parametric vector form, and you want to go to the Cartesian, or the y equals mx plus c form. Let's discuss that quickly. So consider a line L passing through the point A 1, 3, and parallel to the vector V equals 3, 3. Okay. Now this was actually the vector form that I showed you on the screen before. Let me show you. Okay, with this point and this a stretched version of this vector. Okay, actually, let me. Okay, so sorry, a stretched vector, a stretched or compressed multiple of this vector. Okay, so let's get back to the page. Okay, so I'm going to show you that turns out to be the line that we've just been working with, y equals x plus 2. Okay. The parametric vector form is just this then. Okay. And so what we have then is two pretty much simultaneous type equations. And what I can do is eliminate the lambdas and then get x and y in one equation. Okay. So let's eliminate lambda. So if you take one equation away from the other one, then you'll get the following. So let's take the second equation, let's take the first equation away from the second equation. Okay, so again, I've just shown you that this parametric vector form, it reduces down to this line. Okay, so same line, different parametric vector forms. There are infinite ways of parameterizing these lines. Okay, these are the Cartesian forms, and of course there's only one Cartesian form, but they're an infinite way of describing lines using this parameterization or the parametric vector form of a line. Okay, so that's my presentation. Hope you enjoyed it. In other videos, I'm going to be talking about parametric vector forms of a line in 3 dimensions and then higher dimensions. But this, let me just share my screen again with you very quickly. This form works in all dimensions, okay? All right, so if you have any comments, any questions, let me know in the comment section below. Thanks for watching, hope you enjoyed it, and please join me for my next presentation on parametric vector forms of lines in 3-dimensional space. Hope you can join me then.